6.6 is all about measuring heats of reaction. To see how heats of reaction are measured, we can just look at the heat required to raise the temperature of that substance, because the thermochemical measurement is based upon the relationship between heat and the temperature change of that substance. So the first thing we're going to talk about is heat capacity, which is, we use this capital C to represent heat capacity. This is going to be the energy absorbed, which is Q, over the temperature change, which is delta T. For heat capacity, we can define it as the amount of energy needed to raise the temperature of a sample 1 degree C or 1 degree K. So it's important to note when doing these reactions, you could have the answers in degree C or Kelvin. You can do it either way. The other thing important to note, when we talk about heat capacity of the sample, we can talk about per gram or per mole. So heat capacity is C, is Q over delta T. We can also solve this equation for Q, for the heat, is equal to C times delta T. Specific heat gets a little more specific. So we're looking at specific heat being S is equal to Q times the mass times delta T. So the specific heat is dependent on the mass, where heat capacity is not. We can rearrange this equation to solve for Q and make it S times M times delta T. Molar heat capacity now is when we're specifically talking about moles. So in this case, C is equal to Q over N times delta T, and we can rearrange to find Q is equal to C times N times delta T. So different variables are used to represent these heat capacities or specific heat. So we can see C, C sub P, or S. Different texts also use other variables. As I said, this is one of the hardest parts of the heat of reaction chapters, just to figure out what the variables stand for. So make sure, instead of looking at the variables, that you're using the units to help you. So the heat capacity of a sample is just going to be either joules degree C or joules Kelvin, because we don't have quantity involved here. For specific heat capacity, it's going to be joule per gram degree C or joule per gram Kelvin. And for molar heat capacity, it would be joules per mole degree C or joules per mole Kelvin. So again, instead of memorizing the actual variables, it's much easier just to memorize and understand the units. Water has one of the highest specific heats of any water, and this doesn't really say SWATR. It's supposed to be S sub water. So it's the specific heat of water, and it's 4.184 joules per gram degree C. The heat capacity then is, as we said, the energy absorbed over the temperature increase. And we already said that that's Q over delta T. We can rearrange this to find C times delta T. So we're going to now have another equation. Q is equal to S times M times delta T. Those are both from the previous equation. So let's take a look at this problem. It's actually several problems put together. The first problem, they want you to find the heat capacity of a block of metal. They don't tell you what metal, but you know it's 23.04 joules of energy, and the temperature is being raised 12 degrees C. The second part asks again about that same metal. They want to know the specific heat if the block has a mass of 5.00 grams. The third one asks for the molar heat capacity if the metal is copper. And the fourth one says how much energy is given off when 18.55 grams of copper cools from 89.8 degrees C to 21.5 degrees C. Take a look at the next few slides that will help you work through these problems. So the first part of the problem is a simple problem solving for heat capacity. So we're going to use C is equal to Q over delta T. In this case, we know Q is 23.04 joules, and we're going to change the temperature to Kelvin to find 285 Kelvin. When we do the division, we get 8.08 times 10 to the negative second joules per Kelvin. Now we can also solve this for, that's in Kelvin, but we can also do this in simple degrees C. When we solve this, a lot of times you will see them solved in just kept in degrees C. So for this case, it would be 23.04 joules, and this actually should be 12.0 degrees C. And our answer would be 1.92 joules per degree C. So again, it really doesn't matter if it's in joules per Kelvin or joules per degree C, depending on what they're specifically asking for. Since this is in joules and degree C, I might simply leave it in joules degree C. The second problem builds off of the first. Now we know that it is 5.00 grams. So now instead of solving for heat capacity, we'll be solving for a specific heat capacity. And we know that S is equal to Q over delta T times M. All we have to do is plug in all our information and solve to get 0.384 joules per gram degree C. The next step asks us to solve for the molar heat capacity, and they're telling us that it is copper. So in this case, the first thing we have to do is that we know that the mass is 5.00 grams. So we can now convert this to copper by using the molar mass. When we solve that, we get 0.787 moles of copper. Now we simply plug that in for N into our equation, solve, and round to, it should actually be 3 sig figs, which is 2.44 joules per mole degrees C. And that's because this 12 should be 12.0 degrees C. And the very last of this problem asks about how much energy is given off when 18.55 grams of copper cools from 89.8 degrees C to 21.5 degrees C. So our mass of copper is 18.55 grams. Our temperature difference, we take the final minus the initial to get negative 68.3 degrees C. We know our specific heat from part 2, from up here. So now we can just plug it into the equation for specific heat, but solve for Q. When we do this, we will get Q is equal to negative 487 joules. Calorimeters are devices that are used to measure the amount of heat that is either absorbed or given off during a chemical or physical change. One of the most common kinds that we use in laboratory is called a coffee cup calorimeter. It keeps a constant pressure because of the pressure of the atmosphere, so it's exposed to the atmosphere. The coffee cup is usually filled with water or some kind of aqueous solution. We find a lid that loosely fits it, and so that the pressure is the same as the pressure of the atmosphere, and the temperature change is measured. Our enthalpy lab next week will be using a coffee cup calorimeter, and we will be finding Q at constant pressure, which is equal to delta H. So I know some of you were asking the relationship between Q and H, and this is one of them. Q at constant pressure is equal to delta H. Another common kind of calorimeter is a bomb calorimeter. This one now has a constant volume. The reaction is confined to a heavy walled vessel, which we consider a bomb, and the temperature change is measured. So in this case, Q sub V is equal to the change in the internal energy, which is delta E or delta U. I used to do various tests using bomb calorimeters in the coal testing lab. We would take a sample of coal, crushed coal, and put it into a sample chamber, and it would go down into the bomb calorimeter, and when we ignited the sample of coal, we would measure the amount of heat given off. And well, if you look at the next page, there's a nice example of what a bomb calorimeter looks like. This is a typical bomb calorimeter. If you take a look, we have a thermometer here that measures the difference in the temperature. We have a chamber where we put our sample. Inside the chamber, we have wires that go down in. What happens is we have ignition. We have electricity that goes through the wires and creates an ignition from the ignition coil, and that burns off whatever sample we have. The heat from the sample is then absorbed by the water, and the increase in temperature can be measured. When we're talking about calorimeters, they are the surroundings to exchange heat with the system that's being studied. Coffee cup calorimeter, the heat capacity of the calorimeter is determined by the specific heat of the water, because that is what's absorbing the energy created by the system. The bomb calorimeter, the specific heat of the calorimeter depends on the heat capacity of whatever's being used, and it's a given quantity. So oftentimes in this course we'll be using coffee cup calorimeters and not bomb calorimeters. One thing to keep in mind, and it's very important and can be a bit confusing for students, is that the energy of the calorimeter is equal in magnitude but opposite of the energy of the system, because if the system's giving off heat, then the calorimeter is actually absorbing that heat. If the system is absorbing heat, it's absorbing the heat from the calorimeter. So we have to make sure that the sign is opposite of what it is for the system. Take a look at these calorimetry problems. These are typical problems that you would see that use calorimeters, and we will break them down into the next two slides. For the first calorimetry problem, we have a 33 milliliter sample of 1.20 molar HCl, and we're adding that to 42 milliliters of a solution containing excess sodium hydroxide in a coffee cup calorimeter. The solution temperature is initially 25.0 degrees C and rises to 31.8 degrees C. What we're trying to find is the enthalpy change for the reaction, and the reaction is listed here for us. So we're trying to find the delta H for this reaction. One thing to keep in mind is that we're going to have to find the limiting reactant for this. So what I like to do is start off by writing the information I have for each of my reactants. So it's 33 milliliters of HCl, 1.20 molar, and 42 milliliters of NaOH. So if you take a look at this, because it says we have excess NaOH, we know that our limiting reactant is HCl. So the first thing I'm going to do is try to figure out the delta H by doing M times C times delta T. Whoops, sorry about that. And so if I use this equation, if I take the 33 milliliters times plus the 42 milliliters total, that gives me 75 milliliters. And since I'm using a bomb calorimeter, I know I have water, so I can use 1 grams per milliliter for the density of water to find out that I have 75 grams for my calorimeter. Problem. My C for water, the specific heat for water is 4.184 joules per gram degree Celsius. The change in temperature, I have to take the 31.8 minus the 25 to get 6.8 degrees C. So now it's simply plugging everything in. 75 grams times 4.184 joules per gram degree C times 6.8 degrees C gives me 2,132 joules. So this is the heat generated. I need to make it negative for the next step because the heat is given off in the reaction. So if I take 33 milliliters of HCl, change that to liters, and then use my molarity to find the number of moles of HCl. The delta H for the reaction is going to be kilojoules per mole, excuse me, which is negative 2.32 kilojoules over 0.0396 moles, and that gives me negative 58.3 kilojoules per mole. The next part of this problem, or the next problem, is like example 6.6 on page 241. So a 0.562 gram sample of graphite, which is carbon, is placed in a bomb calorimeter with excess of oxygen at 25.00 degrees C, and the sample is ignited. The temperature rises to 25.89 degrees C. The heat capacity of the calorimeter is 20.7 kilojoules per degree C, and we again have to find delta H. So in this case, our balanced equation is just basically taking the graphite, adding the oxygen, and creating carbon dioxide. So it tells us we have excess amount of oxygen, so our limiting reactant is carbon. And again, we're trying to find the delta H. In order to find the change in temperature, we take the final temperature minus the initial, and we get a very small change in temperature, 0.89 degrees C. Our mass is given to us, it's 0.562 grams of carbon, and our C-cal is given to us also, which in most cases this happens when we have a bomb calorimeter. It is 20.7 kilojoules per degree C. So to find Q for the reaction, it is going to be negative C over, times delta T. So we take 20.7 kilojoules per degree C times 0.89 degrees C to get negative 18.4 kilojoules. Now to find the delta H, we have to figure this per mole. So 1 mole of carbon is what we have from this balanced equation, times 12 grams of carbon per 1 mole, times negative 18.4, which is what we had for Q, over 0.562 grams of C. So our answer then is negative 3.9 times 10 to the second kilojoules, and that is what we could write up atop for delta H.